So now we're moving more into the fun side of things. This is more of the maths and more of the actual sort of chemistry. So combustion reactions. So combustion reactions are essentially under this general formula. You put a hydrocarbon in, or your fuel, with oxygen, so you just environment. Carbon dioxide plus water comes out. So both of these are fossil fuels. That's why when we burn fuels, we release fossil fuels or greenhouse gases. No, not fossil fuels, sorry, we release greenhouse gases. I always get those two words mixed up. We release greenhouse gases, apology. So as you can see here, this is a combustion reaction for ethanol. So we've got ethanol here, could be bioethanol. We put the bioethanol in, we have oxygen in there, and then out comes CO2 and H2O. Now, this is in a liquid form. If this is in a gaseous form, this is a greenhouse gas because water vapor is a greenhouse gas. In a liquid form, it's not really. If it becomes a gas, then we say it is. CO2 definitely is. So that's where we get sort of our greenhouse gas emissions from this. So really important. We balanced everything out here. I'm sure you all know how to balance, but just one of those things. So practice question. Let's write out the equation for the incomplete combustion of heptane. So the answer was there. I always forget that I've put the answers in there, and I've put them in there as a transition. So I think what's really important here is incomplete. So what I'm trying to teach you here is essentially what is the difference between complete and incomplete. Incomplete occurs when there is not enough oxygen present. So let's just say we're combusting fuel in an airtight fuel tank. But when we have that airtight fuel tank, there's a little bit of oxygen in there, but there's not enough to combust it all. So what happens is a little bit of chemistry happens, and the fuel goes, all right, well, if we can't combust us all, we may as well combust as much as we can and produce the byproducts that allow us to combust as much as we can. So we put down heptane. Heptane is 7. So that'll be 16, I believe. No, that's on a C. Why don't I put a C there? Apologies. 7H16. And this will probably be in an aqueous form. And then we have oxygen. So that's what we have present. Now, we don't have enough oxygen present, which is the issue. So what are we going to produce? Well, we're going to produce this. We're going to produce carbon monoxide. So if you've heard of carbon monoxide poisoning, the cause of carbon monoxide poisoning or the production of carbon monoxide is not enough oxygen being present. Exactly the same thing here. Then we're also still going to get H2O. So essentially in this one here, instead of producing carbon dioxide, we get carbon monoxide. So now we need to go and balance this. If I want to balance this, I'm going to balance my carbons first. So I'm going to put 7 here. Then I want to balance my hydrogens. If I want to balance my hydrogens, I want 8 here. So I've got 7, I've got 8. That's going to be an uneven number, so therefore I'm going to have to then double it. So I would go 2, I would go 14, I would go 16, and then I would have 14 here, I would have 16 here, I'd have 30, that means that needs to be 15. And that one there, they haven't actually given me a balanced. Oh, incomplete. There you go. So, as you can see there, this is the incomplete, which matches up mine, even though you can barely see it there. The only thing they haven't done is they haven't doubled the equation. They've left this as a fraction. Now, I personally always double mine, but it's not necessary. Some teachers will tell you it is. If I was a teacher, would tell you it is. I think leaving it as a fraction is really poor chemistry. We don't get half molecules. So always double. In my mind, I will say always double, but a lot of people will tell you not to worry about it. So again, preference of what your teacher wants, something that you should ask them. But in a VCAR exam, either one is accepted, even though it's poor chemistry. This at university level wouldn't be accepted because you don't get half a molecule. That's reality. So at VCAR level, either is accepted, but I would always double it. I remember I did this ages ago and I was like, I should change that, and then I never have. Now, thermochemical equations. So, as you can see here, we have the exact same combustion equation, but we have added energy to the end. Now, What that means is that all of these combustion reactions release energy, which is the whole point of it. So we put a fuel in a car because we want the energy, we want the wheels to spin. This is what is happening. We combust the fuel and we get energy out. So these are known as exothermic reactions, and they release energy. However, we do also have things called endothermic reactions. These absorb energy. Fuels don't ever do this. Fuels are always an exothermic reaction, and we'll discuss these in a little bit. But exothermic fuel. Fuel is exo because it releases energy. So as you can see there, all combustion reactions are exothermic. So let's say we combust two different fuels, methane and ethane. So I have the two there again. I have a fraction there. Sure, these reactions tell us that when we combust both methane and ethane, energy is released, but they don't tell us how much energy is released. So we need to get the exact values. Now, where do we get these from? We get these from the data booklet, and we call these enthalpy. So enthalpy is H, and that equals energy. So enthalpy is represented by the letter H, and essentially what we say is that when we have high energy, we have a high enthalpy. On the other hand, we have a low enthalpy, and essentially we would represent this one as a H. So it's stored within the bonds, etc. Yeah. We didn't put the delta H there. Don't worry, we'll do that in a little bit. As you can see here, what we've got is an exothermic equation. Now, why is this exothermic? Because, as you can see here, we started out with our reactants. So these are our reactants. So these are what we're starting with. We start with methane, we start with oxygen. We combust them. The combusting is happening here. We then have our products. Our products have a lot less energy. So they have a lot less energy than what our reactants have. So all of this energy in the middle is referred to as delta H. And why do we call it delta H? Because delta, which is this, means change in. So change in enthalpy. We had this much energy to start off with, we had this much at the end. This difference is the change in enthalpy. It's also the energy released. So that is the energy released out. So as you can see here, when it's exothermic, the reactant is always greater than the product because we need to have energy released out. So because the products are less here, energy has to have gone somewhere. And the delta H is the products take the reactants. So it's kind of like the opposite way. What does that tell you? It tells you that the delta H is going to be a negative value. The delta H will be a negative value for exothermic reactions. As you can see here, we have methane, we have O2, it goes to CO2, 2H2O, and the delta H must have been negative 890 kilojoules per mole. So what that's saying is that 890 kilojoules were lost here if 1 mole of methane was combusted. So 890 kilojoules per mole is the enthalpy, but the change is negative because you're losing it. It doesn't mean that the energy is a negative energy. You can't have a negative energy. There's no such thing. What we're saying is that we had energy removed. Energy went elsewhere. And that's essentially what happened here. Endothermic, on the other hand, is the opposite. So what we've got here is, well, what reaction is this? Have a quick think. What do you think this is? It's photosynthesis. So we're producing glucose and O2 from CO2 and water. So it's literally the exact opposite of like a cellular respiration equation. That's because it is the opposite. It's the plant, and the plant uses the water and the CO2, and it produces glucose. But essentially, as you can see here, this is a very energy, this molecule here has lots of energy. So given that, it's going to be really high up here, but neither of these molecules have that much energy, so they're going to be pretty low. So therefore, the delta H is the opposite. It's going up. Therefore, by going up, we're going to say this is positive because energy had to be absorbed in. It's taken energy from elsewhere and absorbed it in. Therefore, we've added energy, so it's a positive, and our delta H is always going to be greater than 1. It consumes it, it brings it in, Therefore, the energy within the system is now greater, so we say that it's a positive value. So delta H here will always be positive for endothermic reactions. So for combustion, always going to be negative. So enthalpy is measured in kilojoules per mole. And why is that? Essentially, what we're saying is that we've talked about mole 1,000 times. I don't need to go through moles too much. But essentially, what we're saying is that for every mole, we produce this much energy. However, as you can see here, we had 2 mole at the front. So, as much as this is still per mole, this is how much was produced from the 2 moles at the front. So if this had a 1 out the front, or like nothing out the front, this would have been half of that. That's just because we're representing what was shown in this equation, and what was shown in this equation was there was 2 here. So we make up thermochemical equations in 2 parts. What's really important is you only ever have to write a thermochemical equation down if you are specifically asked for a thermochemical equation. If they ask for just a chemical equation of a combustion reaction, do not give the delta H. Why is that? I don't want it. They're asking for a chemical reaction. They're not asking for the thermochemical aspect. They're just asking for the chemical aspect. And that's really, really important. So this part here goes with this, and it only goes there if it's asked for a thermochemical equation. So the other thing, thermochemical equations can be manipulated. So if we double the coefficients, we double the delta H. If we, as you can see there, so we started off with 2 here, we went to 4, we doubled it. If we reverse the equation, we then have a negative delta H. So as you can see here, we had the equation of photosynthesis, we flipped it to make it cellular respiration, we now get a negative. Now, if it had been this one that had been flipped up here, this would have become positive. And then if you add 2 equations, you just add their delta H's. So this has happened in a VCAR exam before. They've asked you to do this. So that's why it's something you sort of need to know how to do. So if you add 2 equations, you add them together. Now, what I mean by that is if I'm adding them together, if they're 2 negative values, I add 2 negative values to each other. It's just going to be an even smaller negative value, essentially. A bigger number, but it's going to be more negative. If you add a positive and a negative one, you just add it like a positive and negative. So don't try and manipulate your negatives and your positives. Just do it as they ask you to do it. Now, key point, don't forget the delta H sign. That's wrong. That's right, etc. So I think this is a really good practice question. I think everyone should have a go at this one quickly. So what you have here is you have enthalpy changes in the formation of ozone, and they ask you from these 3 equations to get to this equation here, and what they are asking for is the delta H of this final reaction. So this is a 5-mark question. It really isn't going to take you as long as a 5-mark question. It came out of one of my 8 notes ones, so it's one of our more difficult ones, but I think it's actually very reasonable at this time. So I want everyone to take sort of maybe 1 or 2 minutes, maybe 3, and have a go at this. So on your notebook, have a go at this question here. Try and get to the correct value. So essentially what you're doing is you're using these equations to get to this equation, and then what you're going to do is get your delta H. So have a go at this. All right, so let's have a look at this one here. I think I've given you enough time. So essentially, if we look at this here, what have we got? We've got an equation that starts out, oh, I didn't mean to do that, starts out with N2O4. So we have N2O4. We finish with nitrous oxide, and we have O3, which is ozone, as our last. So what I like to think about is I like to sort of label out my equations as my starting point. So I'm just going to get a different color. I'm going to get rid of this, and I'm going to get a different color. So we have equation 1. Now what needs to happen to equation 1? I have this as the only thing that sort of matches up. Neither of these are in my other equation. So what needs to happen is this needs to get onto that side. So I need to swap this one. So I'm then going to rewrite it out. I'm going to say I would do this down here in my sort of my working out, because you want that to be part of your working out. But essentially there are some answers already written out, so that's why I'm not putting it down there. But I would swap it out, and I'd get N2O for gas goes to da-da-da-da-da, and I'd get a delta H is equal to negative 11.1. Now, the next one, I don't want to flip it because it's already on this side, but I'm pretty happy with it for now. I'm probably going to have to change up the values of it, but I'm happy with it for now. I'm not going to go ahead and do anything to it yet. And then with this one here, I want to get my O3 on this end. Again, I'm happy with it for now. I may have to multiply it or divide it, but for now, 2 and 3, I'm not going to do anything to. Then what I would do from there is I'd add 1 to 2, and then I'd add the product of that to 3. And you're going to do some manipulating with the numbers, as we will show in the answers here. So as you can see, we've flipped that, and we've got our answer. This one here, we've halved. So we've halved it because we want to get one of these N2Os. Next one, again, we halved it again because we only want one of these O3s. So essentially, we add these first two together, they cancel out. This one's actually gone and added them all together at once. And as you can see there, when you add them all together at once, you end up with this as your final maths equation, and you end up with your answer of 213 kilojoules per mole. So I would have personally gone through and added them 1 and 2, and then the product of 1 and 2 to 2 and 3. However, in this case here, they haven't, because they've just gone through and done it all at once, which you're welcome to do as well. You'll still get your full marks for that. The most important thing here is understanding that this, and this needed to be in those forms, and they needed to be by themselves. They need to be on the right side, or the correct side, the right or left, whichever one is the correct side. And that's how you go about that question there. So there were the answers there, and very nice. So heat of combustion. So when we discuss heat of combustion, what I said before is that we're going to go to our data booklet. As you can see here, your data booklet, which is going to be your best friend, by the way, has the heat of combustions and the molar heat of combustion, so kilojoules per mole and kilojoules per gram. You're always going to use kilojoules per mole unless they ask for you to use this. It's just there in case they ask you to. But you're always going to use this one in case they ask for this one. And the molar heat of combustion, as you can see, is all here. It even gives you the state that it will be in. So depending on what it is, you'll find what state it is in. And you can see there your value. So you may get asked to write a thermochemical equation for ethane, but you're not given the molar heat of combustion. And you'll be like, well, what do I write down as my delta H? I'm confused. Well, you go to your data booklet and you'll find it's here. So sort of the next part here is the universal gas law. So I'm not sure if you will have seen this before because it's been explicitly added to the 1-2 study design, but I don't think it was beforehand. So some of you may have seen it, but some of you may not. Essentially what I refer to this as is the Pivot reaction, and the Pivot reaction is PV equals nRT. Now, the most important thing today is to know what the units are. So pressure is in kilopascals, volume is in liters, N is in moles, R is a constant. Now, 8.31 is sufficient. You don't need to put the 4. If the question explicitly asks you to go to 3 decimal places, you'll use the 4. However, 8.31 is sufficient. You can just use 8.31. Temperature, kelvins. Now, quick point on kelvins. Kelvins is degrees Celsius plus 273. Now, why is that? Someone will say to me, why would I bother with degrees Celsius plus 273? Why can't I just use degrees Celsius? Degrees Celsius is amazing. Degrees Celsius, so much better than Fahrenheit, first of all. At 0, what happens? Water freezes. At 100, what happens? Water boils. It just makes sense. Degrees Celsius is a really, really logical thing. And why is that? Because it was created a lot later on. Degrees Celsius was only really something that was created, I think, through the 18 or 1900s. Kelvins was what we used sort of at the same time, as created around the same time, but it was also created just a little bit earlier. We used it a little bit earlier. And why is that? Because we discovered that if we go as cold as possible, as cold as we possibly can, negative 273 degrees Celsius is the lowest temperature you can possibly get something to. You cannot go any lower than that. I'm sure there are some chemical explanations for this. I don't know them, to be honest with you. I don't do chemistry at university level, so I don't know the answer to why is 273 the lowest value you can get to. I'm sure there is some explanation. If you want to know, go and search up on the internet. You're welcome to. But negative 273 is the lowest possible temperature we can get to. So kelvins has 0 as the lowest possible temperature we can get to. It doesn't have negatives. There's no negative kelvins. You only get to 0. And then from there you add on. So that's why kelvins is the thing. It's used lots in chemistry because in chemistry we work at really low temperatures. So it's better to work at 100 Kelvin than negative 173 degrees. So make sure you use the correct units. I put a practice question in here. We're not going to go through that because we're sort of running out of time. But this is a really good sort of practice question for this topic in terms of that it goes through each of the different points of this equation. Now, do I talk about, just quickly, no I don't. One other point with this is we have this equation that looks like this. V equals N times Vm, I think it is, or Vn. It's Vm or Vn, one of the two. I've forgotten what it is, I apologize. This equation here is a derivative of this equation here. Now I'm gonna get rid of my little scribbles. Now, what do I mean by that is, I'm sure you've all heard of, and if you haven't, that's okay, SLC conditions. SLC. Now, SLC refers to standard laboratory conditions. Standard laboratory conditions are 25 degrees Celsius or 298 Kelvin, 1 molar concentration, and 100 kilopascals of pressure. What that means is if we're doing an experiment and we want to compare things, and I'm sure you all know your sort of constant variables, your constant variables need to be things you're not manipulating, need to stay the same. When we're doing experiments, we like to have things at SLC because SLC just makes sense. If you have things at SLC, you just are always comparing with other things at SLC. Those things are not going to change the results of your experiment. So if we look at this, if I'm doing experiments at SLC, oh, I did that. Apologies, everyone. Bring that back. Your 298 Kelvin, should be capital K, I think. Capital K? Yeah, it's capital K, yeah. Your 298 Kelvin goes in as your temperature. So we now have 298 here. Your 1 molar concentration isn't really in this, so don't worry. Your 8.31 is always going to be the same because it's a constant. It's always going to be 8.31. Your pressure is going to be 100. So if I then look at this, I only have 2 values left. I essentially have 100V equals, I'll do it very quickly on my phone, sorry, 8.31 times by 298. Essentially we have 2,476.38 N. That's what you have. You have an equation left. Now, if you continue to do this, what you end up with is this equation here. V equals N times 24.8. So, if you are given a question and they give you 25 degrees. They give you 100 kilopascals. They give you 8.31. And then they give you a moles or a volume, either one. They'll say maybe the volume is 2 liters, and they want you to find the moles. You could go ahead and plug it into this big equation here. Or you could go, oh, I already know that I'm at SLC, so all I need to do is go 2 liters equals N times 24.8. Or the other way around. If I'm told I have 2 moles, I go volume equals, or we'll say 3 moles, not to confuse everyone, 3 moles times by 24.8. Find my volume. So this is another equation that is really, really useful, and it's in the VCAR data booklet. It's in the VCAR study design. However, VCAR will ask questions about this, and the one resounding comment they will make in their examiner's reports is that most students will still use this big long equation rather than going ahead and saying, hey, this is at SLC. I can just use this quick one here, which is what you should be doing. So really important, know this equation. It's at SLC conditions, which are standard laboratory conditions. And essentially, you do a lot of this, a lot of universal gas equation in terms of fuels, because as we go back just very quickly, notice how a lot of these fuels are in gas state. So when these fuels are in gas state, if you think about your thermochemical equation, you have your hydro, or your fuel, and in this case, it's in a gas. You have your O2, which is also a gas. You have your CO2, which is also a gas. And then you have water. Now, what's really interesting about water is it's most of the time it's a liquid. However, in some cases, it can be a gas. And VCAR will sometimes just give you a combustion reaction where everything is a gas. Therefore, as you can see, they also mention SLC here. Therefore, these questions here where they give you everything as a gas, they'll go ahead and they'll be like, everything is a gas, and you go through the question. You then get to here, and you need to start utilizing this equation because they're going to ask maths questions that require this equation or require this one down here, which is technically this one here. That VM is 24.8, by the way. That's what we refer to that as. So that's the universal gas equation. Really, really important. The second most important thing, so we had the comparison question. That's the one thing I want you to take out of it. If there was 2 things you're taking out of it, take out the units. Know what the units are. Know kilopascals, liters, moles, kelvins, and 8.31 is your universal gas equation constant. However, this is in your data booklet, so you don't need to worry too much about that, but you will know it by the end of the year. You'll do so many questions on this. But you need to have everything as kilopascals. You need to convert it to kilopascals if it's not, and there are conversions in your data booklet. You need to have everything as liters. So if it's mils, it needs to go to liters. You need to have everything as moles. If it's a mass, you then need to convert it to a moles. If it's temperature and it's degrees Celsius, you need to convert it to a kelvins. And what do you think VCAR does? VCAR loves to give you everything in different units because they want to trick you. They will do it. They always give it in atmospheres instead of kilopascals, or they always give it in mass instead of moles, or they always give it in degrees Celsius instead of kelvins. It's ridiculous. People get really frustrated about it. It just is what it is. VCAR loves to do it. But that's essentially what it is.